Hey everyone, and welcome back to part 3 of this video on Bernoulli's equation. In this part, we're going to be going through a worked example so you can see how the equation is used in practice. This will be based on our theory from previous videos, so if you don't understand something, I suggest you go back and watch them first. But with that being said, let's get straight into the problem. So here we have a pipe full of water flowing from left to right. We're going to use our Bernoulli equation to compare 2 points on the same streamline along the center of this flow. The first thing we can notice in our pipe section is there are 2 clear changes in geometry. The pipe rises by a certain height and then significantly expands in diameter. So let's assign some values to these changes. We're given the information that the pipe rises by 4 meters and that the diameter changes from 1 meter to 5 meters. Now, we're going to use our Bernoulli equation to compare 2 points along this pipe section. So let's mark them as locations 1 and 2. Now, we're given some initial data to begin our problem. We're told that the speed of the water at location 1 is 4 meters per second, and that a manometer at this location gives us a pressure reading of 400 kilopascals. What we're trying to work out is what is the pressure at location 2. And we're going to do this using Bernoulli's equation. Now, this is a big equation and it may appear daunting at first, but let's go term by term and you'll see how it's not that complicated. Let's begin with our static head terms. This is the energy due to height. So let's clean up our screen of everything we don't need for this part. When calculating the static head at a location, we do this by measuring its distance from an arbitrary height reference line. We can really place this line at any height we want, and the static heads will simply be measured as a distance from this line. So let's say we place this line 2 meters below location 1. The left-hand side value of our equation would be 2 meters, and the right-hand side 6 meters. And we can simply put these values into our equation, as you can see top left. We could also have placed our height reference line a little higher, so the distance could be 1 meter on the left-hand side and 5 meters on the right-hand side. The key here is that it really doesn't matter where we place this line as long as both values are being measured to the same line. As we're really only interested in the difference between the 2 sides, which in this case is 4 meters, it is common practice to place the line at the height of the lower of the 2 locations. So our static head value on one side will simply go to 0. So these are our static heads resolved. Next, let's move on to resolving our velocity heads. For this part, we're interested in the velocity value given to us for location 1 and the diameters at the 2 different locations. So firstly, we can put into our left-hand side the velocity value given to us at the start. Now, to solve for our velocity at location 2, we're going to draw on our knowledge from flow continuity. Firstly, we're assuming that there are no leaks and therefore nowhere else for the water to go but along the pipe. Therefore, we know that the amount of fluid, known as the flow, which passes by location 1, must be the same as the amount of fluid which goes by location 2. Now, we remember from flow continuity, the flow can be calculated by multiplying the velocity at that location with the cross-sectional area of the pipe at that location. And this allows us to re-express our first equation as V1A1 equals V2A2. Now, you may be wondering, how is this helpful? I don't have the area of the pipe cross-sections at either of these locations, but we do have the diameters. As we know it's a circular section, we can use this rule of geometry to convert the diameter into an area. And therefore, simply by plugging in our corresponding numbers, we can determine the values of A1 and A2. And we now have 3 of the 4 values in this equation. And we can simply rearrange it for our value of V2. Now that we have our value of V2, we can simply put it into the right-hand side of our Bernoulli equation. Now, don't worry, we're nearly there. If you remember, what we were trying to work out the whole time was, what is the pressure value at location 2? And we should have everything we need to do that now. Firstly, G, our constant due to gravity, is 9.81, as we're assuming this pipe section is located on Earth. And rho refers to the density of the fluid in question, which in this case is water, so the value is 1,000. With those values, along with P1, which was given to us at the start, we have all the values to simply plug them into our equation and then rearrange for our one unknown, P2. Upon calculating the value, we see that the pressure at location 2 is lower. This was probably to be expected, as a higher pressure would be required at 1 to move the water up 4 meters of height. Now, hopefully you've been able to follow this example and you feel somewhat more confident with how to use Bernoulli to solve a problem. If you'd like to test yourself, you can find 3 simple example questions with worked solutions in the description of the video. So have a go, put your understanding to the test, and I hope to see you in the next video.